In this video we're going to go from the rotation of a simple cube to the rotation of any function of two variables. So a two variable function will give us a surface in 3D space. So we also want to go on and rotate that surface. And these are some of the examples which I have generated already. Let's say we want to generate a function of two variables, x and y, and we'll call that function, for example, sine of x times y. So we have our two variables, our x-axis and our y-axis. The output is going to be sine of x times y, so the output in effect would be our z-axis, which would be coming out towards us from the screen. So this would generate a surface in 3D space. But as you can see, the tool just doesn't do anything. It won't accept a function of two variables in this form. So in this video, we're going to work out how to generate this type of function and also rotate it in 3D space, which is mapped onto a 2D surface. In order to generate the function of two variables, we're going to use parametric equations. So let's say, for example, we wanted to generate a circle. Then we could write x squared plus y squared is equal to 1, and it will give us a circle of radius 1. Now we can also put a point on the screen just by typing in 1, 1, and that gives us a point. But then what we could do is, rather than have a point here, we could replace each of the x terms and each of the y terms with a function. So let's say, for example, we replaced them with simply the function t and the function t. So in this instance here, the tool knows that the value t is in effect a parameter, and it runs from 0 to 1 in this case. So what it's saying is that the x components are given by the function x is equal to t, and the y components are given by the function y is equal to t. So it means that the x components are, for example, 0.5, and then the y component becomes 0.5, and we have a point here, and the x component goes all the way up to 1, and then the y component goes to 1. So we have this point here, and it just maps all of the points along this value for the parameter t. So another example of this is generating the circle. So in order to generate the circle parametrically, we can simply write in cos t, comma, sin t. And again, it gives us the circle here, and this is the circle given by the parametric equation cos t and sin t. But of course, we're not going to get the full circle. We're going to have to go all the way from not 0 to 1, but 0 to 2 pi. So we're going to use this form of generation of functions, which is the parametric functions, in order to generate this function of two variables. And it's best seen just by working through our process to generate that. So let's go ahead and we'll do that now. Now, a disclaimer: the next couple of equations I didn't generate by myself. I found them online, and then I unravelled how they work, and I'm going to describe them to you now. So what we want to be able to do at first is generate a grid in the x and the y plane. So a lot of lines that run in the horizontal direction and a lot of lines that run in the vertical direction. Now you'll see later on in the video why we want to generate this, but let's just generate them now using a parametric equations. So we're going to introduce another couple of functions. So the first one is called the floor function. So if we had, for example, g of x is equal to floor of x. Now x is just the equation y is equal to x. So it takes this line here and the floor function rounds down to the nearest integer. So for example, if we were to zoom in here, you can see here that the height on this is 0.23, 0.24, and so on. And it takes those numbers and it rounds it down to the nearest integer. So as it goes all the way up close to 1, it actually rounds that down to the value of 0. And then whenever it goes between the value of 1 and 2, again it rounds that down to the value of 1. And when it goes from the value 2 to 3, it rounds it down to the value of 2, and so on and so forth. So we're going to generate all of these little lines here. So that's the first function we're interested in. Now the other function we're interested in is the modulus. So if we have, say for example, h of x is equal to mod of x, and you have to put in a value of, say for example, 1, you'll see that we're going to generate this other set of lines here. So what the mod function does is it does a division and it calculates and then prints off the remainder. So if we look at our y is equal to x, and we take one point here, for example 1, 1, then it does 1 divided by 1, which is a value of 1, and the remainder is 0. So it plots off the point down here, which is 0. If we go to any point here between our 1 and our 2, again it does the 1 divided 1.465 divided by 1, which is 1, and the remainder is 0.465. So it just comes down here and plots off the 0.465. And it does that for all the points between 1 and 2, and it does the points between 2 and 3, and it just keeps generating this set of lines. So these are the two functions here that we're interested in, and these are the two functions we're going to use in order to generate our grid. So let's put in our parametric equation, say for example h of t, comma, g of t. Now it's already generated this here, and it's the blue line from 0 to 1, so it's just this little line here, and you can see how that's been generated because the h of t here is just the x component, and x component is given by the height of this function. So the height of this function here between that point and that point runs from the value of 0 up to 1. So it just runs from 0 up to 1, and that 0 up to 1 gets plotted along the x-axis. And the height of the output is going to be given by g of t, which is this floor function here. And that floor function you can see is just a value of 0 all the way from 0 to 1. So that just gets plotted along there. So it means that the length of the function runs from 0 to 1, and the height of the function is always 0. So we just end up with this single line here, which is not very interesting. So now let's see what happens if we were to introduce a gradient of m. So now we're doing the floor and the mod, not of x but of mx. And you can see here that we would have this line, which is y is equal to mx. Now we're going to be generating not just one line, but we're going to be generating a second, third, fourth, and so on and so forth. Now if we look and see what happens to the value of this function here, you can see here that we're going to be generating the lines as previously, but they're going to become tighter and tighter. So it's not exactly what we're looking for, but we can see the sort of beginning of the formation of a grid. We're getting the lines that we require. But we don't really want the lines to run off from 0 all the way up to infinity, so this is line 1, 2, 3, 4, and so on and so forth. We want all of the lines just to be generated within one region. So a neat little option here is if we divide this whole thing by a value of m, and you can see here that we're getting exactly what we're looking for. We're getting the lines which are going to be generated between the value of 0 and 1. So that's part of the way there. Now, if we wanted to generate the vertical lines, all we need to do is change this function roundabout. So we could go Control C, Control V, but now we'll change that to G of t, and we'll change that to H of t. And now you can see we've really got what it is we're looking for. We've got a grid being generated from the parameter t, which runs from 0 to 1. So that's really quite cool, and we're almost finished on this video. What we're going to do is we want to take this grid and we want to place it at the centre here. So what we can do is we can take off 0.5 for this one, and again we can take off 0.5 for this one. So it now centres the grid on 0. But now you can note we have one line missing here at the end and one line missing here at the end in the horizontal direction. So we can generate those lines by adjusting this to m plus 1 and also adjusting this one here to m plus 1. So now we're going to get the entire grid. Now the last thing we want to do is adjust the size of the grid. We can do that by introducing a new variable n. So we'll put n in here and we'll close the brackets off at the end. And we'll also put n in here as well. And we'll close the brackets off at the end. So now this new variable n allows us to adjust the size of this. Now another thing to note here is the value of m takes on every rational number, and we don't want that. We only want integer values. So for example, what we want here is for this value m to go from 0 to say 400, but in definite steps of 1. So it means when we adjust this, we only get the definite integer values. And the very last thing with our equations is a scaling. You can see here we've got a value n is equal to 1.5, but the actual value here is actually 0.75. So what we want to do is double it so that this goes up to the minus 1.5 and plus 1.5. So we can do that by multiplying by the value of 2 here. So we've got 2n and 2n. So that's our final grid here. And this is us finally generated what it is we want. We can create a grid using parametric equations, and we can make that grid as detailed as we want. And we can also adjust the size of the grid to take up the whole screen. So that is just a beautiful little piece of mathematics, and it's the key for us generating a three-dimensional function. So we will finish off by just tidying this up. We can come in and create a folder, and we can call this folder Grid Equations, and we can stick our two grid equations in here. And we can create a folder called Outputs, and we can put our two outputs here as well. And you can see obviously we can split the outputs into the y coordinates and the x coordinates. So that's us finished off with this video. We've generated a grid using the parametric equations, and we can adjust the resolution of the grid and also the size of the grid. So that's all for this video. What we want to do on the next video is rotate this grid.